be your round trip times the bottleneck link capacity. If you just looked at the second goal, you would say your window should be no larger than the receiver's advertised window. And if you looked at the third goal, you would say your window should be no larger than the sender's congestion window. Okay. So given these three goals, how would you combine them into one window size? Yeah, so the desired window size at the sender is the minimum of the windows that you compute these three ways. In practice, your congestion window will always be less than or equal to the round trip times the bottleneck link capacity. Remember, we said that's an upper bound. And so in practice also, it's a little difficult to actually know what that bottleneck link capacity is. It's not, routers don't tell you this is my capacity. And so in practice, when we implement window sizing, it's the minimum of the receiver advertised window and the congestion window. Any questions on this? Are we good? Okay. So quick recap, what the transport layer tackles: demultiplexing, which we do through logical ports; reliability, for which we have everything we talked about in our last lecture; translation between abstractions. Specifically, we're going to focus more on between packets and byte streams; avoid overloading the receiver, which we do with the receiver's advertised window; and avoid overloading the network, which we do through this congestion window. Okay. You good on that? For any application that either doesn't need reliability, has very short messages, so doesn't have to worry about sequencing and in-order delivery, there is UDP, which is the user datagram protocol. It's a very minimal protocol. It basically just has source and destination ports. Okay. It's just acting to pass back data through to the application. So with that, I was going to start on TCP. Are there any questions, lingering questions on the transport layer in general? So the question is, do TCP and UDP share the same links? Yes. And
how would you like the TCP terms to minimize not congestion?
Right, so that's actually a great question, but it's also something we'll get to when we talk about congestion control, is that in TCP you have a congestion control algorithm that's trying very hard to do the right thing and to be fair in how it shares resources. UDP has no congestion control algorithm running. So in principle, if we had a large number of applications running UDP, running on top of UDP that were not worrying about how much of the network resources they're consuming, they could cause congestion, and they could, in fact, be unfair to TCP. So there is a lot of work. There's also a lot of kind of watchdog monitoring that happens to make sure that there isn't someone hogging all of the network capacity. And ISPs will have certain ways of rate limiting, but in principle, this is something that has happened and can happen, which is if tomorrow YouTube decides to run without congestion control, we'd be in trouble. Yeah?
How does the receiver divide the buffer space between different senders?
That's a good, typically when you open you have a certain amount of buffer space and you'd allocate it on a per connection basis as you set up connections. It's really up to how your operating system, how it's configured, how you want to assign that buffer space. Yeah.
When you run this application, how do you tell your computer to use TCP or UDP?
So typically when you'd open a socket, you open a socket that is of either connection or connection list type, and that tells you. Any? Okay, so moving on to TCP, and when you start on TCP, you have to pay respect to Windsurf and Bob Kahn, who were the two who actually wrote the first TCP implementation. You've probably heard of them. They are Turing Award winners for the work they did on TCP. They won the Turing Award. They won the Presidential Medal of Freedom. Is that Medal of Freedom? Medal of Honor. Sorry. My lack of being born in the US is showing here, which is basically the highest civilian award that the president gives. They've won pretty much every award you can imagine for the work they did on TCP. Interestingly, they actually started building TCP when they were students, when they were graduate students first at UCLA, continued the work on when they were at Stanford. If you ever meet a networking person who's French, they will tell you that actually their job description when they started was to port an implementation of reliability that had been done for the French research network, the equivalent of the research network that was being built in the US, and that became the internet. That is actually true, but be that as it may, probably the most interesting and impactful porting job ever done. So they really built what is, the baseline for our TCP implementations today. Why do we study TCP in fair depth? I think for two reasons. The one, the obvious reason is it's not an exaggeration to say that pretty much the entire internet runs on top of TCP. So clearly it's a critical part of the infrastructure. It's, if you think about somebody who's a developer for Linux or Microsoft Windows, they probably lose sleep over the thought that maybe there's a bug or there's a security vulnerability in their TCP implementation. Because if you have one of those, you're not just taking down one application, you're taking down all applications. Right? So TCP really does play this crucial role. And also, IP is the other part of the story, but if you look at your operating system or the end host, IP is pretty simple in its implementation at the end host. In IP, all of the complexity is in the network and the control plane of the network, BGP, routing, and so on. Whereas in TCP, all of that complexity really is at the end host. So particularly from a security standpoint, it's that much more crucial. The other reason we like to talk about TCP is it actually is a good exercise in kind of engineering excellence and paying attention to detail. We talk a lot about high-level approaches and design principles and even design solutions, but it really, when you work through the details of TCP, you get an appreciation how even a fairly simple design actually needs a lot of attention to detail in how it's implemented. And lastly, your second project is on basically implementing a TCP-compatible reliability protocol. So the protocol you implement will actually be TCP-compatible, that it could speak to a real TCP implementation on the other side. And so we go into a fair amount of detail so that the project is also easier. With that, where I wanted to start was the TCP abstraction. Okay? So we've said this a few times, that TCP delivers a reliable in-order byte stream. Okay, so let's unpack that a little bit. What that means is that if you're at the application layer, you see a stream of bytes, application data, that you're sending from host A to host B. Okay? There's a byte. It's a stream of bytes, so every byte you can think of it as having a number, and you're going to deliver it in order to the receiver. If we dig into how that's actually implemented a little bit now, you're not sending one byte at a time to the receiver. Instead, you're taking a set of these bytes from the application, and you're going to put it into what we call a TCP segment. And we send TCP segments over to the receiving side. So a TCP segment is the actual application data or the TCP data that's being sent between hosts. Okay, and typically you'd accumulate, how many bytes do you send at one time? Or what's the size of the segment? You'd have a value that we call the maximum segment size, and I'll get to it in a minute. So typically you send bytes in chunks of either you accumulate a maximum segment size or MSS worth of bytes, and you send it over, or until a timer goes off. Why do we have the timer? For the obvious reason. What if your application had only 10 bytes to send, and your MSS was 500 bytes? You're not going to sit there forever waiting for more bytes. So you have a timer that says, this is as many bytes as I have to send in this time. I'm going to send it out as a TCP segment. So digging into the TCP segment a little bit more, when we talk about a TCP packet, it looks like what I have up here. And a TCP packet is always an IP packet because all packets are IP packets. But inside the payload of the IP packet, you have a TCP header and you have a TCP segment, which is the actual application data we're carrying. Okay? So we know that the IP packet should be no bigger than the maximum transmission unit of the link at the sender, the MTU. And so that tells us that a TCP segment, or the MSS size, has to be set to be the MTU minus the length of the IP header minus the length of the TCP header. Okay? Any questions here? All right, so this is pretty straightforward. Let's go back to our picture. So we said we're going to transfer bytes, or this byte stream, from A to B in these TCP segment chunks. Okay? That's the TCP data. We're going to put a TCP header in the front because you have to be able to explain what those bytes are to the receiving end. And in particular, the field that we're going to have to carry in that header is a sequence number that tells the receiver where in that byte stream these bytes fit in. Okay? Does this make sense? Right, so now we're going to just change notation because TCP does things a little specifically, in a rather specific to TCP way here. The notation change we're going to have is that previously we focused on packets. I send packet number 1, 2, 3. When I get an acknowledgement, it's saying I acknowledge packet number 1, 2, 3. Right? So we were saying there's like a number associated with every one of these packets. The thing to really internalize is that TCP doesn't think about packet numbers. TCP just thinks in terms of bytes and that byte stream. And so a packet is identified by the bytes that it carries, where they belong in that byte stream. So a sequence number is, I am byte 158 in the byte stream. And an acknowledgement says, I received all bytes up to 259, as an example. And when I talk about windows, it's not about how many packets you can send into the network. It's about how many bytes you can send into the network. This trips people up invariably, especially on exams. You should be comfortable reasoning in terms of packets or bytes. Particularly when we talk about TCP, it's usually we're talking about bytes and byte streams. But if we ask you about a reliability protocol we're making up where you have packet numbers, you should be comfortable going back and forth between those. So let's walk through what these sequence numbers look like in a little bit more detail. And let me first step through what it does, and then we'll come back to why it does things this way or how. Okay. So in TCP, your byte stream doesn't start out as being numbered byte 0, byte 1, byte 2, byte 3. Instead, what we say is that every connection, you start numbering at what we call an initial sequence number, or ISN. This is randomly picked for every time you start a connection. You pick a new random ISN number. Okay. And your first byte in that byte stream is numbered ISN plus 1. Okay, so not ISN plus 0, ISN plus 1. And I'll get to why in a minute. When you then take a chunk of those bytes and send it out as a TCP packet, your sequence number is the offset of the first byte in that segment. Right? So if you were k bytes past the beginning, you'd be ISN plus k. Yeah? And when you acknowledge, what TCP will do is the sequence number that it sends back in its acknowledgement to the sender is the first byte after all the bytes that have been received. Okay, so it's what we call the next expected byte. So in this picture, if the receiver has received all bytes up to this point, whatever the offset is for that green byte, that is what the acknowledgement number is going to tell you. Any questions on just clarifying what this is doing? I'll get into why in a minute. Okay, so idiosyncrasies of TCP start with an ISN. First byte is numbered ISN plus 1. Sequence number is the offset of the first byte in the packet, and your acknowledgement is the next expected byte, or the first unacknowledged byte. So why does TCP do things this way? Anyone can guess why would you pick a random initial sequence number as opposed to just starting from 0? Prevent overlapping. Any other? Yeah. You can't just fake a connection by, yes, you're absolutely right. Let me get to that in a minute. So the original motivation for having an initial sequence number was the scenario that Cerf and Khan were worried about was, let's say I open a connection between a source and destination, and then I kill the connection and immediately restart it. For whatever reason, right? The application decided to kill it and restart it. If you just restarted with the same initial sequence number, everything else that defines that connection is also the same, the source and destination port, the source and destination IP address. So they were worried about, I restarted a connection, it's a new connection, but I have packets in the network that belong to the old incarnation of that connection. Okay? So that was why they first had this initial sequence number. Then the initial TCP implementation actually had the initial sequence number would be plus 1 what the previous initial sequence number was, or it was augmenting by some time value. And then people found that you could actually launch an attack by guessing what the initial sequence number was. So it's a fairly involved attack. For those of you who are interested, Google it, you'll find the description. There's actually an RFC that describes it. But it was very sneaky because it would allow you to appear to be the client talking to a server, even if your client actually could not hijack or snoop on the original client's traffic. So it's pretty involved in the setup because you have to first manage to hide traffic from the true client and then at the same time be able to look like a legit client to the server. So that's the reason why we have now randomized initial sequence numbers. Any questions on that? I don't expect you to.